Hi everybody, I hope this video finds you well. In this video we're going to be working through the two questions on the correlation and regression practice sheet. You can find this practice sheet posted on your guys' course website. I would highly recommend that if you haven't already to work through these two questions on your own to make sure you're comfortable with them. If you have already worked through them, then this video will just be running through the questions, quickly seeing how to do each piece, and you can use it to sort of check your work and make sure that you're comfortable with the things covered in this practice. So there's sort of two questions on this. First of all, we've got that we're studying the relationship between the number of people in a group and the time it takes that group to complete a series of puzzles or tasks. So to do this, you conduct an experiment where you first divide people into randomly sized groups. So we had some groups that only had like 1 or 2 people, some groups who had as many as 8 and 10. And then you record how long it takes each group to finish their set of puzzles, right? And you get those completion times over here in minutes. So we're going to do all the standard stuff. We're going to draw a scatter plot, calculate the correlation coefficient, get the LSR, talk about the LSR, make some predictions, and look at the residual plot. So let's go ahead and take a look at all those pieces here. So we've got our sort of data here. We're going to go ahead and start by trying to do the scatter plot. Now keep in mind, before we actually start that, we do need to identify the explanatory and the response. Clearly in this pairing, the number of members should help explain the completion time. So we know that this is going to be our explanatory. Let's just zoom in a little bit. That'll make it a little bit easier to sort of read there. That'll be our explanatory, and of course that means that that'll go into L1 when we're ready to use the calculator. And this will be the response, the completion time, and that'll go into list 2. All right, so we can go ahead and start drawing our scatter plot. So give yourself your quadrant of an axis there, of a coordinate axis. Then this is going to be our explanatory variable, which is the number of members here. And looks like that ranged anywhere from 1 up to 10. So we can just go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we'll just label those real quick. All right. And then for the completion time, you'll notice we have a high of 105 and a low of 54. So maybe we can go 50, 60, 70, 80, 90, 100, and 110. So this will be completion time. And we said that that's going to be 50, 60, 70, 80, 90, 100, and 110. Now, of course, you'll notice that right here, this is all the numbers from 0 to 50 sort of squished together. So we should use that little squiggly line to indicate that that part of the axis has been condensed. All right, let's start drawing our points. We had 1 and 105, so it looks like we've got a point way up there. We've got 2 and 73, so it looks like maybe a point right about there. And then 2 and 76, so probably right about there. Then we've got 3 and 67, so right about there. 5 and 60, right about there. 5 and 61, just directly above it, right there. 6 and 58, so it looks like maybe right about there. 7 and 59, so right about there. 8 and 55, so right about there. And then we've got 10 and 54, which looks to be right about there. So there's our sort of scatter plot for this data here. Okay, let's jump right into getting the correlation coefficient. Obviously for the correlation coefficient, you'll need to put this data in L1, this data into L2, and use that ln reg AX plus B. I believe my data is already in there, so we should be able to get that pretty quick. And if we do that, the correlation coefficient that we get, we should get R is approximately negative 0.8036. Well, we get a negative value here. Does that make sense? Yeah, because generally speaking, we're seeing a negative relation here that as the more members we have, the lower that completion time, which makes sense. The more people you have, the faster you should be able to get the stuff done. This is a pretty decent correlation coefficient, right? Negative 0.8 is pretty close to negative 1. We can check if it's strong enough by using table E. So let's go ahead and do that. Table E. we had 10 data points. We know that because they said that they had sort of 10 different groups, but we can also just count 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we do have 10 data points. We can look that up on table E all the way here. Remember, we take our n is 10. We always use that 0.025. We intersect them, and that gives us our critical value, 0.6319. So we'll go back, and this should tell us that our critical value is 0.6319. Then we will compare. We'll take the absolute value of r, which is going to be necessary because r is negative here. We'll compare that. Absolute value of r would be 0.8036. That is certainly larger than the critical value, which implies there is enough evidence for a, well, and we know that it is a negative correlation, In other words, we are convinced that the number of members is associated with how long it takes. And that association is a negative one, meaning generally speaking, as the number of members increases, the completion time decreases. All right, the next thing I believe we wanted was to go ahead and get that LSR, right? So let's go ahead and write that down. So the LSR, of course, that also just comes from your ln/reg AX plus B. You should get that y hat is negative 4.2x plus 87.4. And I'm just choosing to round everything to one decimal to keep it easy here. Now, of course, this is good algebraic format of the LSR. You're welcome to keep it like that, or you can replace them with their variables, right? So we're saying that the predicted time is negative 4.2 times that group size plus 87.4. And again, the only advantage of this sort of format here is just to remind you what the variables were. All right, we wanted to draw this thing. So to draw LSR, we need 2 points. Well, a starting value, you could use 0, you could use 1, whatever you sort of prefer. Let's just go ahead and use 1 here. So x equals 1. Then that would give us y hat is negative 4.2 times 1 plus 87.4, which sounds like it's going to give us 83.2. We'll put that in another color there. So our point here is going to be 1 and 83.2. We can graph that one on there. 1 and 83.2 seems to be right about there. And again, I would recommend using a different color or a different notation because remember, this point isn't a data point. It's just a prediction from our model. All right, let's go ahead and do another one. So sort of end of our axis was 10, so we'll try to use that guy. X equals 10, that gives us y hat is negative 4.2 times 10 plus 87.4, and if we do that, sounds like that should give us about 45.4, which means our second point we want to use is 1045.4. Now, you should immediately sort of see that this 45.4 is going to give us a little bit of trouble because 45.4 is going to be somewhere in that sort of squiggly line. But remember, that whole section has been condensed. So we can't really use this 45.4 because we don't know exactly where it should go in there. In other words, it's not part of the area where we actually have our good scale. So, of course, you could go back and you could redraw and maybe add on, so, like a 40 and a 30 or something like that to make this doable. But, of course, our scatter plot's already in place. So probably the easiest thing is just to use a different x value. Remember, we can choose any x values we want, so we might as well choose something that's sort of easy for us. So we'll not use this guy, and instead we'll go ahead and we'll use, let's go back to our normal color here. Let's just use x equals 8 because that'll be a little bit easier to do. So we can get negative 4.2 times 8 plus 87.4. We type that into our calculator, negative 4.2 times 8 plus 87.4. We should get 53.8. So that point would be 8 comma 53.8. And that should be drawable, right? 8 and 53.8. 8 and 53.8 should be somewhere right about there. All right, now we can go ahead and connect our two sort of points there, right? There we go, right? So there's our sort of line. And of course, if we wanted to, we could even extend it a little bit further out, right? Just to sort of keep that. So there we go, right? A little bit of an issue just because that first point that we wanted to use didn't really fit on our axes, but we recovered pretty nicely by just choosing a different point there. Remember, you guys are allowed to choose any x values that are convenient for you, so just pick whatever sort of works nicely. All right, let's go ahead and talk about the slope as well. We can fit this in on this page. Oh, my apologies. That's a little too much there. All right, let's go ahead and talk about the slope. All right, the slope, of course, as a value is this guy right here. So the slope is negative 4.2. And we know algebraically the slope is when you go up 1 in x, this slope is what happens to y. Since it's negative, it would mean going down 4.2y. So let's think about what those things would mean, right? Going up 1 in x means, well, x is the number of members. So when you go up 1 member, right, we're expecting the y, which is the time, to go down by 4.2. So you would go down 4.2 time. Well, let's try to write that as a sentence. Our model predicts that for each additional group member, the completion time will decrease by 4.2 minutes. So in other words, for every extra group member you add, or every extra person you add, the completion time will decrease by about 4.2 minutes. All right. Now, notice that we're in the problem not asked to talk about the intercept. And the reason we're not asked to talk about the intercept is that the intercept wouldn't make a lot of sense. Because remember, the intercept would be about when x, or the number of members, would be 0. But of course, you can't have a group that has nobody in it, so we're not going to even bother talking about the intercept. So again, this is just a reminder that slope is something that always makes sense, but intercept may or may not make sense depending on the situation. All right, we wanted to make one prediction, and we'll go ahead and do that on the next sort of sheet here. So for F, we wanted to do the completion time for group with 4 members. So since this was a prediction, we're just going to plug in, right? That time is predicted to be negative 4.2 times the group size, which in this case is going to be 4 plus that 87.4. We can calculate that, negative 4.2 times 4 plus that 87.4, and you should get 70.6. So a group with 4 members should finish in 70.6 minutes. Can we trust this prediction? Well, the explanatory range was from size 1 up to size 10. 4 is definitely right in there, so we can trust this. Trust this since size 4 is in that explanatory range, which was from 1 up to 10. Okay. All right, last thing we want to do is we wanted to do that residual plot. Now remember, the residual plot has those residuals that are going to be y minus the predicted. So we're going to need to add some columns to our data. So to do that, I'm going to come back up here where I have my nice data sort of written out and add those 2 columns. So I'm going to have the sort of predicted time here, and then I'm going to have the residual here. And remember that the residual is just simply going to be the values here minus the values here. How do we get these predicted times? Well, anytime you want a prediction, you just go ahead and use your model. So for each of these things in the predicted time, we're just going to take the number of group members, plug it in there, and use this equation to calculate those predicted times. So let's go ahead and do that. We'll get negative 4.2 times 1 plus 87.4. And the first predicted time should be 83.2. Then we'll do negative 4.2 times 2 plus 87.4. The next predicted time should be 79. And then, of course, it's going to be 79 again. Then for group size 3, it'll be negative 4.2 times 3 plus 87.4. So you should get 74.8. Then for group size 5, negative 4.2 times 5 plus 87.4. That should be 66.4. Then 66.4 again, because the next one also has group size 5. Then group size 6, so negative 4.2 times 6 plus 87.4. That should be 62.2. Then the 7, negative 4.2 times 7 plus 87.4. That would be 58. Then the 8, negative 4.2 times 8 plus 87.4. That's 53.8. And finally, the group size of 10, negative 4.2 times 10 plus 87.4. That should give us 45.4. So those are our predicted times there. Now we will go ahead and calculate the residuals by just taking the actual completion times minus those predicted ones. So 105 minus 83.2, first residual we get is 21.8. Then 73 minus 79, we should get negative 6. Then 76 minus 79, we should get negative 3. Then 67 minus 74.8, we should get negative 7.8. Then 60 minus 66.4, we should get negative 6.4. Then 61 minus 66.4, we should get negative 5.4. Then for 6, we've got 58 minus 62.2, so we get negative 4.2. Then for 59 minus 58, we just get a 1. And then 55 minus 53.8, we get 1.2. And then finally 54 minus 45.4, we get 8.6. Now, to actually build our residual plot, we use our explanatory and those residuals. So let's go ahead and do that. So there's our plot. This is going to be the residuals here. Remember to float your 0 in the middle there. Then pick just a pretty loose scale. Looks like we got to make sure that we can put 21 on there. So we can just go by sort of tens. There's positive 10. There's positive 20. There's negative 10. There's negative 20. And then remember that this should be your explanatory. So this will be our group size down here. And we just had 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we'll just label those. And let's go ahead and graph this stuff. So our first one was group size of 1 and a residual of 21.8. So that would put us somewhere way, way up there. Then we had a group size of 2 and a residual of negative 6. So it looks like we should be somewhere right about there. And then also group size 2 and a residual of negative 3. So that would put us right there. Then we had a group size of 3 and a residual of negative 7.8. So maybe right about there. Then we had a group size of 5 and negative 6.4. So that seems to be right about there. Then we had a group size of 5 and negative 5.4. So that seems like it should be right about there. And then we had a group size 6 and negative 4.2, which sounds like it should be right about there. Then we had group size 7 and a residual of 1. So we have something right about there. Then group size of 8 and a residual of 1.2. So it looks like maybe right about there. And then a group size of 10 and a residual of 8.6. Okay, so remember, when you're looking at a residual plot, you're hoping that everything looks nicely scattered. What you really don't want to see is you don't want to see a U shape or an upside down U shape. Well, what do we see here? We unfortunately do see that sort of strong U shape. It continues down here and then out through there. So we see a pattern to residuals. That tells us our linear model is not appropriate. And actually, since we're seeing that U shape or that upside down shape, it actually tells us data is actually exponential. Now, again, for us, all we're really trying to do is build this residual plot and figure out if it's appropriate or not. This extra statement that the data is actually exponential, that's just something we're making as a comment. But do keep in mind, if we look back at the original scatter plot, you can see why that's the case, right? If we look at those original data points, they sort of followed something that definitely had a negative direction, but more had a curve rather than that straight line, right? It sort of started off very steeply decreasing and then started to go more shallow. That's exponential in nature. So there we go, right? That sort of runs you guys through all the major things you should be able to do with correlation and regression when given sort of raw data like this. All right, let's go ahead and look at question 2. Question 2 is a little bit different because in question 2, we don't have the raw data. We're instead taking a look at sort of a summarized version of the information. So in question 2, we're talking about studying how advertising affects the number of customers that a shopping center gets each week. To study this, you go to the shopping center for 16 weeks. Each week, you record how much the center spent on advertising in thousands of dollars and how many customers visited the center that week. So you get the following sort of regression line. We get y hat is 215x plus 730, where y is the number of customers who visit that week, and x is the spending on advertising in thousands of dollars. So here we're treating y, the number of customers, as the response, and x, the spending on advertising, to be the actual explanatory. We're also told that we get an R value that's about 0.52, and we're also told that the lowest amount that they ever spent on advertising in 1 week was $2,000, while the most was $8,000. So we're going to work through a couple things like this, talking about is there evidence for a correlation. We'll talk about the slope and the intercept. We'll talk about the coefficient of determination. We'll make a prediction, and we'll calculate a residual. So this will be very similar to the previous one. The only big difference here is we don't have the raw data. Instead, we have the sort of summary of the analysis of the data and of the LSR here. So let's go ahead and take a look at doing these pieces here. So first, is there enough evidence for a correlation? Why or why not? So we know for A, we have an R that they told us was about 0.52. That's what was stated in the question. To compare that, we need to go on to table E. To do that, we need to know the amount of data. Now, obviously, in this one, we don't have raw data, but in the question, it said that you visited for 16 weeks. So we know that N is 16. If we take a look at table E, we have N being 16, we have 0.025, and we can see that the critical value is 0.4973. So let's go ahead and record that. The critical value here is 0.4973. So we can compare, we can take the absolute value of R, which isn't necessary because it's already positive, but we can just do that anyway. And we can see that the absolute value of R just barely makes it in over the critical value. So it just barely makes it in over that critical value. That does tell us, though, that there is enough evidence for a positive correlation. How do we know it's a positive correlation? Well, because the correlation coefficient originally was positive. All right, so not a super strong relationship here. 0.52 is not super close to 1, but since we had 16 data points, it is enough to say that there actually is evidence for a correlation. All right, let's talk about the slope. Well, if we go back to our model real quick, the slope, of course, is this value here, so it's that 215. So the slope is 215. Algebraically, the slope means that when you go up 1 in x, that slope value is what happens to y. So we go up 215y. Now we need to remember what these variables represent. Well, going up 1 in x, x was about the amount spent on advertising. But we need to be careful about the units here. It specifically said that it's not dollars, it's actually thousands of dollars. So this means that when we go up $1,000 on advertising, well, the y here was supposed to be the number of customers. Then we go up 215 customers. So now we just want to try to say that in a sentence. So we would say for each additional $1,000 spent on advertising, our model predicts an extra 215 customers will visit the center. Okay. So in other words, our model is telling us that for about every extra $1,000 this shopping center will spend, they should get about an extra 215 customers. All right, let's talk about the intercept. The intercept, of course, is the other value that makes up the LSR. So in our actual model here, it would be that 730. So that's our 730. Algebraically, the intercept is always about when x is 0, then that intercept is y. So y is 730. So what does it mean for x to be 0? Must make sense here because we were being asked to do it. So if we do $0 on advertising, technically 0,000, but 0,000 is just 0, then we expect to get 730 customers. So it might sound a little bit weird, but it should make sense. This is basically saying if they don't advertise at all, they still expect to get some customers, namely 730. So if the center doesn't spend any money on ads, they expect around 730 customers. So even if they don't spend any money, they expect to get about 730 customers. Then as they begin to spend money, we know that they should gain about 215 customers every $1,000 they spend. So again, notice that the slope and the intercept really tell us everything we need to know about our model. All right, we wanted to also get coefficient of determination. Remember, coefficient of determination, that's just a fancy name for r squared, which in this case is 0.52 squared. So we can calculate that. 0.52 squared should give us 0.2704. If you're asked to interpret the coefficient of determination, make sure to always do it as a percentage. This would mean 27.04% of variation in the response. What's the response? Well, in this case, it's the number of customers. In the number of customers can be explained by changes in the explanatory variable, which in this case, in the amount spent on advertising. So in other words, what this is telling us is that our model accounts for a little over a quarter of the variation. So in other words, a quarter of the variation in how many people show up can just simply be explained by saying, oh, we advertised more this week, we advertised less this week, etc. The other sort of 3/4, or more specifically the other 72.96%, that cannot be explained by the advertising. It must be due to other factors. All right, we wanted to make a prediction, right? So customers when 15,000 is spent on ads. Okay, that means since we're doing a prediction, we're gonna be plugging that in. We do need to be careful though. Remember that X is in thousands. So X here is going to be $15,000. So when we go to plug in here, we get our predicted Y is going to be 215 times 15 plus 730. And again, remember that 215 and that 730, that's just coming from the original model there. We're plugging in 15 because it's talking about $15,000 spent on advertising. So let's go ahead and calculate that. 215 times 15 plus 730. Right, so that looks like we should get 3955. So if they spend 15,000 on ads, they expect 3,955 customers. Okay, would we trust this prediction? Well, to trust, we have to know the explanatory range. So if we move back to the original question, we can see that they told us the explanatory range. They said that in 1 week, they spent as low as 2,000 or as high as 8,000. So unfortunately, when we're making a prediction about 15,000, we're not able to trust this prediction. So cannot trust this since 15,000 is far outside the explanatory range, which was 2,000 up to 8,000. So unfortunately, we just never had a week in our data set that was close to 15,000. So while we, are able to mathematically plug it into our model, the prediction that we actually get there doesn't necessarily make a lot of sense, nor can we really trust it. All right, last part here, right? We wanted to calculate a residual. There was a data point where they spent 6,000 and had 2,250 customers. So keep in mind that this right here, that is our X, and that right there is our Y. If we want to calculate the residual is Y minus the predicted. So we need to know, what does our model think should happen when we spend $6,000? So let's actually calculate that. Y hat is going to be 215 times, again, remember, don't plug in 6,000. Make sure to plug in $6,000. So X will be 6. All right, plus that 730. And when we do that, 215 times 6 plus 730, looks like we should get 2,020. So that's our predicted value. So the residual here would be the actual number of customers, 2,250, minus the predicted, 2,020, which looks like we should get 230 customers as the residual. So if we also wanted to make a slight more interpretation, we would say that the mall sort of overperformed in terms of customers, right? According to our model, if they spent $6,000, they should have only gotten about 2,020 visitors, but they managed to get 2,250 visitors. So that was 230 more customers than anticipated.